All right, welcome back grade 12s to our continuing discussion of genetics. In this episode, we're going to be talking about pedigree charts. We're also going to be talking about different kind of genetics that would be considered perhaps non-Mendelian, where we're going to have a different interaction of genes than our straightforward dominant and recessive situations. And we also need to talk about what happens when we have more than two forms that a gene can take, and that's going to lead us into talking about multiple allele situations. So starting with pedigrees, you'll be able to read this slide for yourself. Essentially, pedigree charts are ways that we can look at a family line of traits and individuals that may have the traits or may not. You can kind of think of it like a bit of a family tree. So a pedigree chart is going to show us several generations of a family, and those generations are going to be shown particularly here. We have the first generation, we have right here, and then our second generation is connected by a line, and it's right underneath the first generation. We could have a third generation, and so on. We're also going to see who marries into a family. So we can see right here that this line is telling us that perhaps this woman, represented by a circle, is marrying this man, or at least is going to mate and have offspring with that man. We also can tell the gender. Like I said, circles are for females and squares are for males. We also will see mortality. You can't see it on this legend, but usually if an individual dies, we would see a diagonal line across the individual. All right? And we will see individuals affected with a certain disorder or whatever trait we happen to be looking for, because they're going to be shaded. So shaded means that they have a particular disorder that we might be talking about. And also we could see the presence of twins as well. Identical twins versus non-identical twins. To be honest, it doesn't show up too much in many of the pedigrees that you'll be looking at. So let's look at why they're useful. Pedigrees are useful for determining inheritance patterns. So is a disorder, is it recessive or is it dominant? Does it happen to affect a specific gender, like males more than females? We would be able to see all that in a pedigree. Also, genetic counselors would use that information to help a couple make informed decisions in terms of what are the risks to their offspring having certain disorders. So let's take a look at an example. This is a recessive pedigree example. Now, how do we know it's a recessive pedigree example? Well, we can see that these two normal parents have an affected offspring. Now again, we could put in some genotypes and phenotypes. So let's take something like tongue rolling, for example. Now, we know that tongue rolling is, not being able to roll your tongue is a recessive trait. So for example, those would be the genotypes of our parents, because let's say they can roll their tongues. They're not affected with the disability or the fact that they can't roll their tongues, right? And so these are tongue rollers. That's their phenotype, and there's their genotype. And we notice that this is an affected son. Squares are boys. This is an affected son. And so to be affected, if it's recessive, the only way to have the trait is to be homozygous recessive. Little r. And so when we look at a pedigree, we can determine if the trait is a recessive trait or not. And it must be in this case, because it's the only way that an affected individual can have two typical or normal parents. Also, recessive traits skip generations. So we don't see the trait of not being able to roll your tongue in the first generation, but it reappears in this generation. Okay? Now, if we look at the next slide, it's the dominant pedigree. Now, how do we know that it's dominant? Because we see the trait in every generation. So it is possible, for example, Hodgkinson's disease is a dominant, caused by a dominant allele. So in this case, if you were normal, or you did not have Huntington's disease, you would be little h, and then this individual has the dominant disorder. So let's say we know they have the big H, but we're not sure what that is, because they would have the disorder if they were homozygous dominant, big H, or big H, little h. Now, how would we know? We could go to the offspring, right? Hey, we see some normal offspring here. Remember, to be normal? And so, and we know that this individual would be this situation, okay? So normal means, now remember, where did these alleles come from? From the parents. So one parent gave a little h, and the other parent must have given the other little h. So that confirms that that female is heterozygous, right? And she is affected by the dominant allele. And so that's typical of this kind of pedigree. A dominant pedigree is that we see that the trait is in every generation. It doesn't skip. And if we have an affected individual, at least one parent also has the trait. This is a very complex pedigree of the royal family of England. There's Queen Victoria right there, and you can tell that there's another royal family, a French royal family, I believe, and then there ends up being some intermarriage that brings these two royal families together. And we're looking at a hemophilia disease. Now, hemophilia is a recessive disorder, but it's also what we call a sex-linked disorder, which we're going to be looking at in the next chapter, which will tend to affect males more than females. And if we studied the chart, if we had time to do that, we would see that there's many more males affected with hemophilia than females. And the females are indicated, as a matter of fact, I don't think we have any females that actually have hemophilia, but they all carry the recessive allele. So they're typically normal, but they carry that recessive allele, and they will tend to give it to their sons, all right? We'll talk more about that later. Now let's turn our attention to some non-Mendelian genetics, where we have alleles, but we don't truly have one dominant and one recessive allele. So that happens in situations that are called incomplete dominance and a multiple allele situation, all right? So prior to Mendel's studies, many scientists believed or saw that hybrids, or that there would be these blending of traits. So sometimes two alleles could be equally dominant and interact with each other, and it produces a new phenotype. So we call that incomplete dominance, and it kind of occurs in two different ways. So one way is an intermediate inheritance. So in other words, the brand new phenotype, you can think of it as a blend of the two traits. So two equally dominant alleles produce a new phenotype that is a blend of the two forms, just like blending in paint, in art. So if you have, for example, red and white snapdragons, and you cross them, then the first generation of plants, so there's our parent plants, pure breeding red crossed with pure breeding white, that would result in a blend of pink snapdragons, which is a new phenotype. Neither one, neither red nor white, being dominant over the other one. Now the other situation, or another situation, is codominance. So this is the interaction of two equally dominant genes, and you're going to see both of those genes expressed at the same time. So this happens with cattle, where we have a red shorthorn bull, and we're going to cross it with a white cow. The calf will not be a pink calf, but what we call roan. Roan being intermixing of red and white hairs. So kind of splotchy. But we see red and white intermingled. So that is what we call codominance. So let's see exactly how this looks. All right? Now, when we're doing these kinds of crosses, we can't use the capital letter, little letter, like we typically do for dominance and dominant versus recessive. So what we often do is use a capital letter to represent the trait. And then we use superscripts for the forms that the gene can take, which are equally dominant. So for example, if we used hair color, like with our cattle, then capital H stands for hair, and the superscripts are the two alleles, or the alleles that we can have. So red would be a little r, and white would be a little w. We could make them capitals, but remember, they're sort of equally dominant. So that's why we could use both capitals, capital R, capital W, or little r, little w. You can see the different genotypes that produce the different phenotypes. 2 little r's, red. 2 little w's, white. 1 of each, we get that roan, or for codominance. Now with our snapdragons, we could say, let capital C be for the color trait, and then again, the superscripts are going to be very similar, the R for red, the W for white, when you have one of each blending that incomplete dominance. So we have the pink colored flowers. Now the next slides are going to show you the actual crosses. So for example, remember if we have our red snapdragons, white snapdragons, pure breeding, all we get in the F1 generation is one genotype, which means all of those flowers are pink. But what if we were to do a cross of those pink flowers? Then this is the Punnett square that we would set up with our 2 pink parents. Then we fill in our Punnett square, and we notice that we do get all 3 different possible phenotypes, right? We get 1 red snapdragon, 2 pink snapdragons, and 1 white. So a different than that 3-to-1 expectation with normal Mendelian genetics. Now if we take a look at our bulls and cows, the cattle, again we're going to have our pure breeding parents, red and white. We do the Punnett square, and we notice again that all the F1 offspring are roan, and we just have the one possible genotype. So now, again, let's cross the F1 together. So we're going to take 2 roan cows, set up the Punnett square, split those alleles for the gametes, combine for the offspring, and again we see a typical ratio of 1 red, 2 roan, and 1 white. Now, the last thing to look at is a multiple allele situation. Now, we call it multiple alleles because currently we've only assumed 2 different forms of a gene, right? Capital R, little r, or even with our incomplete dominance. We have a red allele, we have a white allele. But what happens when there's more than 2 options? We call it a multiple allele situation, when there's more than 2 forms. So now with my ice cream cone analogy, you don't just get a choice of chocolate or vanilla. Now there's chocolate, strawberry, and vanilla, right? Or even more options to choose from. So how do Punnett squares work in this situation? Well, let's take a look. So we often pick on fruit flies in genetics because fruit flies are kind of our versions of Mendel's peas. They work really well for doing genetics. So let's say with fruit flies, they can have many different colors of, I think in this case, what are we looking at? Eye color possibilities. So there are 4 different alleles that give rise to their eye color. And so what we do, we're going to use capital E for their eyes, and the superscripts are going to be 1 for red. Now, there is a dominance order for these alleles. That's why the greater than sign. So the 4 different alleles are 1 for red, 2 for apricot, 3 for honey, and 4 for white. And this is the order of dominance. So red is the most dominant allele. Red will show up no matter what the other allele is. Okay? And E2, or apricot, is the next dominant. More dominant over the honey allele, the white allele. So let's just see how this works. So what would happen if we take an apricot male and made it to a red-eyed female? Notice phenotype, genotype. Remember when we do our Punnett square, we've got the male here and the female here. Separate the alleles and then bring them together for the offspring. So there we go there. So hopefully, now let's identify what the offspring are. We know that when we see E1, we're going to have red eyes. So we see 2 of those. Then we see an E2 as the most dominant for that offspring. So that's an apricot eye color. And then we have number 3. Remember, 3 is honey. So this fly offspring is a honey colored. So there's what we expect in the offspring. Now, could we ever have a white-eyed fly from this pairing? No, right? Because although there is the white allele there, there's no white allele in the other parent. So for example, we would never expect to get white-eyed flies from this crossing. What combinations, by the way, would give an apricot phenotype? Well, any combination that has E2, but no E1, because remember, that's more dominant. So E2, definitely apricot, but even E2, E3, because that's the honey allele, but apricot is more dominant, and apricot is more dominant than the white allele. So those are 3 different possibilities that give rise to that same phenotype of apricot eye color. Now, multiple alleles also shows up with our blood system that we talked about in Bio 20. So do you remember, a little refresher? You have the blood type you have. It's genetic because of the markers that you have on your red blood cells. And if you have a particular antigen marker, that gives you your blood type. So if you have blood type O, remember there's 2 possibilities of markers with our ABO system. You can have an A antigen marker, B antigen marker, but maybe you have neither. That's how you're type O. If you're type A, you only have the A markers. If you're type B, you only have the B markers. And remember, you might be able to have them both. And it's genetic. And it's a situation of multiple alleles, right? Because there is an allele for the A antigen, there is an allele for the B antigen, and you might not have either of those, which means you get a recessive allele that doesn't provide you with any antigen of the A or the B. Okay, so let's kind of see how this works. Now, not only is it a multiple allele situation because we have the 3 different forms, but it's also an excellent example of codominance. The alleles that create the A antigens and the B antigens, those 2 alleles are codominant, which means if you have both of them, you will end up with both A and B as your blood type, all right? And then the allele that creates neither is recessive. Now again, what convention do we use for the alleles? We use a capital I, and then we put the superscripts as A, B, and we don't have an I with an O because it's recessive. We kind of do something a little unusual here, and we use a little I for the allele that causes no antigen markers on your red blood cells. So the phenotypes and genotypes set up this way. If you were type A blood, so remember that's kind of your phenotype. Your blood type is type A. I'm type A. Well, what does that mean about my possible genotype? It means, remember now, we can only have 2 alleles for blood type, one from mom, one from dad. So we don't get more alleles. We get a choice of more alleles, but we still only receive 2. So if I'm type A, I could have received both. From both of my parents, I received the A allele. Or I received an A from one of my parents, and then my other parent gave me the recessive allele that creates no antigen markers, but I would still be type A. And then that goes the same for type B. And then in the special case of type AB, it means that from your parents, you get 1 of each. And if you're type O, the only way to be type O is to be homozygous recessive and get the 2 little I's, 1 from each parent. So if we look at some examples here, I'm not going to spend too much time with this right here, which again gives us all those different blood type possibilities. But again, this would be a Punnett square cross example where a parent has the blood type AB and the other parent is type O. And these are the predictions for the offspring. We predict that 50% of the offspring will be type A and 50% of the offspring will be type B. There is no possibility for type O or for type AB. Now in this example, we have a type A parent with a type B parent who's a carrier for that recessive allele. Now we see that we can get 50% of the individuals are type AB and 50% of the offspring are going to be type A. Again, no chance for a type O situation there. So let's say this question simply says, if we had a young lady with blood type O and she gives birth to a baby who is also type O, in a court case she claims that a certain young man is the father, that man has type A blood. Could he be the father of the child? And can it be proven that he alone is the father? Well, what I would do in this question is, I know that the type O woman, so this is our symbol for lady. Let's see if this shows up a little better. So our female, it's not the greatest, okay? Let's try green. That's probably a little better. The female is type O, so she's, we could write it like this, but quite often we could also write it like this, two little I's. And the male is type A, so we know but we don't know for sure what this other option is. It could be another A, or it could be the recessive. And so to answer this, yes, he could be the father of the child, but only if he carries the recessive allele. But it can't be proven on this evidence alone. Okay, so, and when I even though I'm erasing this here, the explanation is still on the slide here. Okay, there's the explanation there, kind of what I went through with you already. Now, the last thing to end on, guys, is that you also know that with our blood types, you can be positive or negative with your blood type. Now, the good news here is that is Mendelian. In other words, we do have two alleles for that trait to be positive or negative. And positive is dominant. We call it the rhesus factor, so we often use RH as our symbol. And remember, the only way to be Rh negative as your blood type is to have two recessive alleles. Otherwise, you're going to be positive with just one positive allele from one parent. Okay? So we simply treat it, as you can see down here, that the phenotype, we would say you're positive or Rh positive. So what are your possible genotypes? You received both positive alleles from each parent, or one positive allele from one parent and one negative allele from the other parent. The only way to be Rh negative as your blood type is to receive both negative alleles, one from each parent. Okay? There we go. All right, guys, so you've got some assignment problems to practice. Please practice. It's the only way to become really familiar and quick with doing the genetics problems.